And particularly this is the Chinese New Year's Eve. So Happy New Year. This week we have the speaker is our colleague Yao, and she's going to speak about small scale formations in the compressible porous media equation. Go ahead, please.
Thank you. So first, I'd like to thank Chun and Andre for the kind invitation, and also for to Ethan and Connor for organizing this wonderful series of seminars. So today I will be talking about a new joint work with Sasha Kiselev about the small-scale formations in the incompressible porous media equation. So let me first introduce to you what that equation is. Let's say that we have some density of the fluid. They are incompressible. And what is special is that they are living in the porous media. Let's think about sand as an example. Okay, so this equation here describes the evolution of the density. We can see that, well, it is not so surprising that it's just the transport equation. The density is transported by the velocity field u, where u is incompressible. Right, and then they are living in the spatial domain omega. So throughout this talk, I'm going to focus on the case that omega lives in 2 dimensions. It could be either the whole plane, it could be the 2-dimensional torus, or it could be a 2-dimensional strips that it is periodic in the x1 direction, but then there is the boundary up and below. So what makes this equation special is the rule that the velocity field is determined by the density. Well, we know from the Newton's law that usually it should be the acceleration is proportional to the force, right? So which can be seen in, for example, the Euler equation. However, in the porous medium like sand, things are behaving quite differently, namely that instead of the Newton's law, the velocity field actually obeys the Darcy's law here, which says that the velocity is directly proportional to whatever force that is dragging the fluid. Okay, and here the only force that is dragging the fluid is the gravitational force, which is pointing downwards, and then it is proportional to the density rho with the proportionality constant given by g. Right, so which we are going to set g to be equal to 1. So that is the force that is acting on the fluid. But meanwhile, that in order to keep the velocity field to be incompressible, we have to correct it by some pressure term just to make it incompressible. So, and then the effect of this pressure term can be seen as one basically performs a Leray projection to project this force onto the velocity field that are incompressible. So you project it into the closest one in the L2 sense. And just intuitively to see what things are happening here, let's say that we have a bunch of positive density here, negative density here, and then the gray arrow would be indicating just the gravitational force itself. And then, however, that this is not divergence free in this whole domain, and then therefore, so these purple arrows indicates that, well, after we project it into the divergence free vector field, so this is what's the actual vector field U look like. And so setting this viscosity constant mu and the permeability constant kappa and also the gravitational constant g, setting them all of them equal to 1, we actually have that the velocity field u is can be determined by the density rho at each moment from this relationship here, which usually people call it Biot-Savart law, to indicate that this is the rule that the velocity field is determined by the scalar being transported. So that is what the Biot-Savart law is. And just to give you an intuitive picture what it looks like, if the density is just a single positive delta function, then it creates a velocity field that looks like that. So it is incompressible, and then it's going downwards over here, and yeah, it looks like that. So that is what this equation is. And so since this is the transport equation where it describes that a scalar rho is being transported by a vector field u, let me compare it to several other equations that looks quite similar in the fluid community. So I'm going to be comparing this incompressible porous media equation with the 2D Euler equation and the 2D surface quasi-geostrophic equation. And the common thing is that all these three equations describes that there is certain scalar here. Usually for 2D Euler, the scalar is vorticity. People usually use omega instead of rho to denote it. But in any case, it describes that the scalar is transported by a velocity field u, and in each of the case, u is determined by certain Biot Savart law from the scalar itself. So these are the Biot Savart law for 2D Euler and SQG. And so all these three are incompressible. However, there are some subtle differences. So for example, if we look at 2D Euler here, then starting from the vorticity, we take the inverse Laplacian and then we take the grad perp, which is the gradient, and then rotate it for 90 degrees to recover u, right? So in that sense, u is one more derivative more regular than the vorticity, right? But as for the SQG, because we only take half of the inverse Laplacian and then followed by the gradient, u is about as singular as rho itself, right? And as for the IPM equation, we have a -2 gradients and then one gradient and one gradient. So again, that u is about as singular as rho, right? So in that sense that the Biot Savart law for u for the SQG and for the IPM, they are comparable because they sort of have the same regularity. And then, this can also be seen as in the Fourier symbol, that the 2D Euler equation, this Biot Savart law has a Fourier symbol of the homogeneous of degree -1, while SQG and IPM are homogeneous with degree 0, right? However, as we will see that because these two Fourier symbols have a subtle difference, that one is even in K and one is odd in K, and these subtle difference actually has some effect in the local well-posedness theory, as we will see later. So regarding the question that, well, suppose we start with a sufficiently regular initial data in a high Sobolev space, then does the solution live in this Sobolev space for a short time? Then the answer by a rather standard argument can be shown to be yes for all these three types of equations. However, when it comes to the global well-posedness, for 2D Euler equation, it has been known since the time of Wolibner and Holder for almost a century that the initial vorticity in a sufficiently high HS space are globally regular. However, this is unknown for both the SQG and the IPM equation. And actually 2D Euler is the critical case here, because if we look at how the HS norm is evolving in time, then one obtains this differential inequality that it is growing with the rate proportional to the L infinity norm of gradient u. And notice that for 2D Euler, because u has one more derivative more regular than the vorticity, gradient u is about comparable to the vorticity itself. And actually, they are related to each other by a singular integral operator. So in that sense, we can't exactly say that its L infinity norm is directly bounded by the L infinity norm of omega, but this is almost the case. There is just a slight difference of a log. And this extra log guarantees that, well, so this HS norm will remain finite for all time for the 2D Euler. However, as soon as the Biot Savart law gets a little bit more singular than that, it is an open question. So that is the comparison for these three equations. And let me review some relevant literature for the IPM equation. So Cordoba, Gancedo, and Orivi proved the local well-posedness of this equation in HS for s bigger than 2. And they also provided various blow-up criteria. So for example, one of them is in terms of, it says that as long as the level set doesn't become oscillating too fast, and as long as the Riesz potential, Riesz transform of rho L infinity norm remain bounded, then the solution remains regular. And Freelander, Gancedo, Sun, and Vico have studied the more singular equation with this Biot-Savart law here, where when beta is equal to 0, this is exactly the incompressible porous media itself. So they are considering the case when beta is even bigger, meaning the Biot-Savart law is more singular. They proved that this equation is ill-posed as soon as beta is bigger than 0, which is actually, so this have something to do with the fact that whether its Fourier symbol is an even or an odd operator, because for the SQG equation, one can actually make it more singular and still having the equation being local well-posed, but not here. However, they proved that if one considers the patch solution, then such solution is local well-posed if beta is slightly bigger than 0. One thing that I would like to mention is that for the IPM, because of its Biot-Savart law that contains a partial x1 of rho, one can easily check that for all the horizontal stratified steady state, where rho is only a function of x2, then every such thing is automatically give us a 0 velocity field. Therefore, all of the such horizontal stratified steady state is stationary, right? And intuitively, we would expect that if the lighter density is on the top and if the heavier density is on the bottom, then such things should be stable, and it should be unstable if it's the other way around. So this has been rigorously proved by Elgindy. He proved that for this steady state minus x2 with lighter on top and heavier on the bottom, not only that it is linearly stable, but actually it is asymptotically stable as time goes to infinity with certain convergence rate towards a steady state. And so his result works in the whole space, and in the bounded strip where it is periodic in the x1 direction, but have a top and bottom boundary in the x2, Castro, Cordova, and Lear proved that. So again, near this stratified solution, which intuitively we would expect it to be stable, they proved that the smooth initial data near this solution is globally regular for the Sobolev space H10 or above. So that is the previous local well-posedness theory. For large data, so far, the question of whether there is global well-posedness is still open. There are some numerics done for the IPM to see whether there could be a blow-up or not. And I'm stealing this nice picture from the work by Cordova, Gancedo, and Orive, where they performed a series of numerical simulations in the two-dimensional torus. And these results suggest that, so this is the x2, the vertical direction. So it seems like as time goes, the solution becomes more stratified, which makes sense, right? Because of the gravity is driving the solution. And these numerics suggest that the gradient of the density could be growing as time goes to infinity. However, that they compare the numerical simulation with their blow up criteria, and they say that, well, there is no evidence for finite time blow up. So together with Sasha Kiselev, our goal is that, well, we were not able to prove whether the solution can blow up or not in finite time. So that was still open. And what we would like to do is that, assuming there is a global in time solution, we want to be rigorously proving that, well, there can be indeed small scale formation as the time goes to infinity. So this is there has been no small scale formation results for the incompressible porous media equation before. However, for some other active scalar equations, such as 2D Euler and SQG, there has been such result. And let me first give you a quick review on these. So the small scale formation of the 2D Euler can be dated back to a long time ago since the Udovich. So he proved that there can be some infinite growth of the gradient of the vorticity, which was upgraded into the linear growth by Nadirashvili. And starting from the work by Bahuri and Shaman, all these more recent work are establishing the small scale formations that comes from the idea of having the initial data very close to a steady state with hyperbolic flow. So the steady state is as follows. If we are in the two-dimensional torus and if the initial data looks like that, so it has this odd structure here, then one can check that, well, this is actually a steady state and it corresponds to the velocity field that looks like this. So and it gets the name of the hyperbolic flow because near this point, the velocity field looks like hyperbolas. So this steady state itself actually is not smooth, right? Because the omega actually has a jump, which means that it has infinite gradient. However, if we ignore this fact and just look at the velocity field, then notice that the particles are approaching each other double exponentially fast in this steady state. Okay, and then so the idea for Denisov and Kiselev, Shverak, and Zlatosh are all based on that, well, they are constructing smooth initial data that are perturbations of this non-smooth discontinuous steady state, such that they argue that, well, quantitatively that, well, this hyperbolic structure is still going to be remaining true in that smooth solution. So that was the idea of these constructions in 2D Euler, and in particular that Kiselev and Shverak shows that in a bounded disk, a smooth initial data can indeed lead to the double exponential growth, which is known to be sharp. And in the torus, the best growth result is by Zlatosh for exponential growth so far. And these are the small scale formation results for the 2D Euler. And for SQG, this is done more recently. So the reason that this is only discovered later is that, well, even though one would intuitively expect that SQG has a Biot-Savart law that is more singular than Euler, and therefore it should be growing more crazily. But actually it is harder to prove the small scale formations because one has, while the parts that is helping the small scale formation grow stronger, the parts that is stopping it also grow stronger. So one have to battle with that. So this is done more recently by Kiselev and Sming He, that they proved that in the torus, a smooth initial data can lead to exponential growth on the gradient, assuming that the solution remain regular for all time, because this is also not known for the SQG equation. Okay, so that is the strategy that is used for Euler and SQG, and as we can see that most of these ideas are based on this explicit hyperbolic scenario steady state. However, such a scenario just doesn't exist in the incompressible porous medium equation. One of the reasons is that, well, because the Biot-Savart law is different, that instead of an odd operator, it's actually an even operator here. So there is no odd-odd symmetry. And instead of that, so it's the if initial data is odd in x2 and even in x1, so this is the symmetry that is preserved for all the time, not this odd symmetry for Euler and SQG. But this is only a minor reason. I would say a more substantial reason is that there just can't be anything like the hyperbolic structure in the steady states for IPM, because one can check that in the whole space, the only steady states for the IPM with a finite L2 norm of U is just this boring horizontal stratified state with the velocity fields that is identically equal to 0. And in the torus, there can be more. So for example, other than the horizontal stratified state, one can also check that, well, these vertical stratified states are also steady states where the velocity field is finally something that is non-zero. However, they are not the trajectories are not approaching each other's, like what is the case in the hyperbolic flow scenario. So this is a more fundamental difference. Together with Sasha, we take a completely different approach instead, and then we prove the following result. So let me first state the results in the whole space R2, and then we also have similar results in the torus and also for the strip. So in R2, let's say that we have a compactly supported initial data that is odd in the x2 variable, and in the upper half plane, we set it to be non-negative. And then we prove that as long as the solution remains smooth for all the time, then the certain inverse power of the HS norm will have a finite integral for all the s bigger than 0. So if we think about the fact that, well, 1 over t, this function is integrating exactly to, has infinite integral, and then we compare these two, then a direct consequence is that, well, the HS norm of rho is growing with certain polynomial rate, well, in the lim sup sense, for all the s that is bigger than 0. And notice that here, this range s bigger than 0 is actually sharp, because when s is exactly equal to 0, then we are talking about the L2 norm of rho, which is actually conserved because the rho is transported by an incompressible flow. So this is our result, and let me briefly mention the idea of the proof, which is done by a completely different approach than all the previous small scale formations. And actually, I would say the proof is simpler, but it only works for these kind of equations that are driven by the gravity. As I described, that the initial data is odd in x2, it is non-negative here in the upper half plane. And one can easily check that the odd symmetry about the x2 variable is preserved for all the time, which means that for all the later time, we are going to have something that is non-negative on the upper half plane and non-positive on the lower half. So the main tool for our analysis is the monotonicity of the potential energy. So the potential energy is defined by just the integral of rho times x2. And so first notice that because we know that for all the later time, we are going to have this odd structure with rho positive above and rho negative below, then it means that one thing we get for free is that this potential energy E is going to be uniformly bounded below by 0 for all the later time. Right. And next, the key step is to show that, well, the potential energy is actually dropping in time, which is intuitively true because the whole equation is just driven by the gravity, right? But let's actually show it. So a quick computation gives that, sorry, we are in R2, so just using the rho is odd in x2, it gives that the derivative is equal to the integral of rho u2, and plugging in the exact Biot sub R law, we immediately have that the derivative is equal to negative of this quantity, which we call delta, which is the h-1 norm of the partial x1 of rho. Okay, so which means that, well, because we know E is monotone decreasing and it's bigger than 0 for all the later time, then immediately we know that, well, delta has to have a finite integral, right? From time 0 all the way to time infinity, which means that this delta has to get small, well, at least in an average sense, as the time gets large, right? So if we take a more careful look at this quantity delta, we notice that, well, first, it's very easy to check that if delta is exactly 0, then this can only happen if rho is a perfect horizontal steady state, right? So formally that we would expect that, well, suppose at some moment we know that delta is not exactly 0, but it is a tiny number, then this can only happen if the density is extremely stretched out in the horizontal direction, right? And if this is extremely stretched out in the horizontal direction, then it means that in the vertical direction, we should be having some very rapid change. Right, so we want to show that at any moment, as long as delta is tiny, it has to mean that at this moment, the HS norm of rho s has to be huge, right? So that is the argument that we want to show, and which is actually doable on the Fourier side. So namely that our goal is to show this very explicit inequality that if delta is small, then for any s bigger than 0, it has to have a huge HS norm, which is more precisely bigger than delta to the power negative s over 4. Okay, and then once we prove this by plugging it into this integrability of delta, we'll immediately finish the proof. It means that because delta is integrable, it has to become small in the average sense as time goes to infinity, and therefore the HS norm has to become huge, right? So that's a very simple idea. And so the way that we show this inequality is by looking at the Fourier side. So notice that the L2 norm of rho hat is conserved, which because the L2 norm of rho is conserved for all the time. And rho hat itself is bounded by the L1 norm, which is also conserved. So it has a uniformly bounded rho hat. And which means that suppose at some moment I have my delta t, which is rho hat square multiplied by this extra weight. Suppose this quantity is tiny, then notice that this weight only vanishes at, it exactly vanishes near the C2 axis, and it gets very small as long as the angle is very close to vertical. Okay, so if delta is tiny, it means that more than a half of the mass of this rho hat has to be concentrated somewhere that is very close to the C2 axis. And as a result, because the total integral of rho hat square is a conserved quantity, so half of them being near this C2 axis means that, well, and it has to be reaching somewhere where the C2 is very high. Right, so for that reason, we can show that, well, with this C2 to any positive power as the weight, then this number must be huge as delta becoming tiny. And therefore, this gives us the lower bound for the HS norm of rho itself in terms of delta. Okay, so that is, it's a pretty simple argument on the Fourier side to show this inequality. And then we just plug it into the integrability of delta. So that is the idea for the whole domain. And if we are having the periodic torus, then we will see that things are slightly different. So in this case, we are still able to prove some growth result, although so in different Sobolev spaces. So namely that we add some additional constraint on the initial data. Not only we set it to be odd in x2, but we also let it even in the x1 variable. And this odd even symmetry is preserved for all time. And for this little yellow square here, we set the initial data inside here to be non-negative. And then we prove that if the solution remains smooth for all the time, then the HS norm is going to have infinite growth for all so the HS norm of the partial x1 is going to grow for all the s bigger than -1/2. So when translating it to the HS norm of rho itself, it means that for any s bigger than 1/2, it will be growing to infinity in the limb sup sense. And notice that once we prove it for the torus, it actually automatically holds for the strip because from this odd-even symmetry that we have set up our initial data, so U will automatically satisfy the no flow condition on the top and bottom, and therefore this is automatically a solution on the strip as well. So why can we show the the growth of HS norm in R2 for all the s bigger than 0, but only for s bigger than 1/2 in the torus? Well, the reason is that, again, we are using the same trick that E prime is equal to, the E is dropping in time with the time derivative given by the minus delta. And so, however, that the difference is that in the R2, our idea was that, well, as soon as delta is tiny, then it has to be that the solution has to be extremely stretched out in the horizontal direction, and therefore that its vertical change must be large pretty much everywhere. Right. However, in the torus, things are a bit different. So namely that even if at some later moment when delta is tiny, which means that so the rho is very close to horizontal in the distribution sense, it doesn't mean that there has to be a large derivative in the x2 variable. So it could be just of order 1. So what we are using here is that instead we show that, well, if the initial data here is pinned down at 0 on the x2 axis, then this property is preserved for all the time, and therefore being close to a horizontal state in the distribution sense has to imply a rapid change in the x1 variable instead of the x2. So, so that is the difference on the proof, and this is for why we cannot get all the HS for s bigger than 0, but only for s bigger than 1/2. But the idea to prove that is also just by looking at the Fourier side to say that if delta is tiny, then the partial x1 of rho has to have a huge HS norm for s bigger than -1/2. Okay, so that is the proof on the torus. For the rest of the time, I would like to discuss the stratified steady state, which all of them are stationary. And I would like to discuss some stability versus instability for these steady states. So notice that for any horizontal stratified state where the rho is only a function of x2, when we are plugging it into the Biot-Savart law, which contains a partial x1, then we know that, well, it is automatically stationary because u is a constant 0. Right. So our question is that, well, what can we say about the stability of such steady state? So in fluid equations, there is a vast literature on the linear stability versus instability for steady state, and also how to upgrade them from the linear stability into nonlinear instability. And in particular that my colleagues Chongchen Zeng and Ji Lin are all experts on these areas. So usually the first step that is done is to just look at what is the linearized equation near each of the steady state. So let's look at the difference between the actual solution with this steady state and plugging it into the IPM. So there is still this velocity field U, and the Biot-Savart law is the same here because the rho s itself has no contribution to the velocity field. So the Biot-Savart law is the same, the way that U is related to eta. However, that there is an extra term here that is contributed by this rho s. Okay, and so this is the fully nonlinear equation for this difference. And if we are linearizing them for a small eta, then this term is quadratic in eta, so this goes away. And the linearized equation looks like that. So here, let's look at this. So I'm plugging in this explicit U2 so that it can be explicitly written as an operator in terms of eta. And notice that this orange part is always a negative operator. So that is intuitively suggesting that, well, if G prime is something that is negative, then this should be linearly stable. But if G prime is positive somewhere, which physically it means if the heavier density is on top of the lighter ones at some place locally, then we would naturally expect that it should be unstable, right? Due to the Rayleigh-Taylor instability in some sense. Whereas if it's always that's the lighter fluid is on top of the heavier one, then intuitively we would expect stability. So this has been rigorously proved. I mean, for the nonlinear equation, in the case where G is equal to minus x2, so that the density is linearly increasing as we go down. And I would say that maybe this exact minus x2 can be replaced by other monotone functions. It's just that having this exact form makes it easier for on the linearized level because this is a constant. So in this case, the asymptotic stability for the nonlinear equation was established by Elgindy in R2. So he proves that, well, if we add on top of this minus x2 steady state, a small perturbation that is small in H20 or above, then not only that there is a global solution which remains close to the steady state, but actually that the perturbation is decaying to zero as time goes to infinity with certain algebraic rate. And then similarly, that Castro and Cordoba and Lear deal with the case in the strip. They show that, again, for this steady state with lighter density on top and heavier on the bottom, then if the perturbation is small in H10 or above, then as time goes to infinity, it exists globally in time, it will converge to another stratified state. However, that stratified state may be slightly different from this minus x2 because any other stratified state is also stationary, right? So it may be driven towards something that is near it, but not quite exactly the same. So these are the nonlinear and actually asymptotic stability result. And our goal is to work at this reverse direction. So we want to show the nonlinear instability for the stratified state in both the torus and the strip. And so usually the nonlinear stability is done by looking at the linearized equation to first prove the linear instability of the linearized equation and then upgrade it into the nonlinear one. However, with such an argument, usually that as soon as the equation is entering the fully nonlinear regime, when the perturbation is getting already pretty large to the steady state, then usually one cannot say much, right? So we take a different approach. We do not use this common approach of upgrading linear instability into the nonlinear one, but rather that we would like to make use of these small scale formation results that we have obtained to obtain the nonlinear stability. And as we will see that these nonlinear stability are infinite in time, in the sense that we can say that, well, the difference between the dynamical solution and the steady state is actually growing to infinity as time goes to infinity. So our first result deals with the nonlinear stability in a torus. We prove that any odd in x2 stratified state is nonlinearly unstable. So namely that let's take any horizontal stratified state that is odd in X2, then no matter how high is the Sobolev space K, we are able to find a small perturbation that is tiny in the HK norm, such that this initial data will lead to a solution. And again, we have no idea whether there will be a blow up or not. So our proofs are all based on the condition that, well, if nothing bad happens, if it doesn't blow up, then the difference between rho t and the stratified state will be growing to infinity in any of the HS+1 norm. So in basically anything bigger than H1 norm. So that is the result. And notice that this cannot be just directly apply our previous proof because our setting there was that the initial data was pinned down to value 0 along the X2 axis. And we cannot create an initial data satisfying this condition that are close to a horizontal stratified state, right? And therefore, we have to find some new approach to it. And the new idea here is that starting from this rho s, we want to be perturbing it a little bit to create a rho 0, where rho 0 is done by perturbing it with some smooth incompressible flow. Okay, so more precisely, notice that for any stratified state that is periodic and that is odd in X2, we know that it can be perfectly monotone on the in the torus, right? Otherwise, it won't be periodic. So it means that there has to be some point at which we call it H0, where locally that we are having heavier fluids that are on top of the lighter one, right? Which means G prime is bigger than 0. So now we want to create a perturbation that is just locally near this point. So using just a circular flow near this point, we obtain a initial condition which is still smooth, and it can be made close to rho s in an arbitrary high Sobolev space with arbitrarily small norm. And the important thing is that we can make it such that the potential energy of rho 0 is strictly less than that of rho s. Okay, so intuitively, this is actually reasonable to expect that because locally that it's the heavier fluids that are on top of the lighter one. This should be a very stable, unstable situation, right? And by rotating it a little bit, then the potential energy actually is going down. So once we have such an initial condition, then notice that, and by the way, the perturbation is actually, it's also symmetric. So because we want to keep the odd structure. And once the odd structure is kept, the potential energy will be monotone dropping. It means that even initially, it is strictly less than rho s. And for all the later time, there has to be a gap from the actual potential energy of the rho t with the potential energy of rho s. Okay, so this gap guarantees that for all the future time, our solution can't be getting too close to rho s. And because rho s is the only stratified state that is topologically reachable from rho 0, it means that not only it never gets too close to rho s, but actually with some extra work, we can show that the level sets can never get too close to any horizontal steady state. And which means that, well, so the integral of this derivative will have an L1 norm that will be uniformly bounded below in time. And therefore, if the H-1 norm of this quantity is integrable, which means that it becomes small in the average sense as time goes to infinity, then we can show that its HS norm of this, the derivative will have to be growing to infinity for all the s bigger than 0. So that is the instability for in the torus. And but you may say that, well, this is not so surprising because any steady state will have locally a point where the heavier fluid are on top of the lighter one, which is linearly unstable anyway. right? Well, but we are actually able to show in this last theorem that even, so let's now consider the stratified state in the strip, right? So in this case, the monotone steady states are allowed. And we know that some of them are non-linearly stable, right? Like this rho s equal to minus x2. We know that this is non-linearly stable by Castro, Cordoba, and Lear in H10 or above. And together with Sasha, we show that, well, if we add there exists a smooth perturbation that is small in the H2 minus gamma norm. Okay, so we can make our perturbation to be small in this 2 minus gamma norm, but not quite in H2 or above. And then for such small perturbation, we show that, well, the solution will have this growth for all the time. Okay, so we don't know whether this 2 is the sharp threshold or not, but comparing it with the previous nonlinear stability result, we know that certainly that's this exponent are not allowed to exceed 10, right? So now it means that for perturbation above H10, this steady state is non-linearly stable. And then we show that if the perturbation is only small in the H2 or something below H2, then there is actually this infinite in time nonlinear instability result. And there, the difficulty is that we cannot, again, none of the previous approach that we have done apply here, because let's just think about this nonlinear stable steady state, where it's always the lighter density is on top of the heavier one. Right. So previously that whenever the heavier one is on top of the lighter one, we are able to locally perturb near this point to make the energy to be dropping a little bit and to set such thing as the initial data. But this strategy will never work for such a rho s, because this is among all the distributions that are reachable from rho s by any smooth flow. This is already the guy with the lowest potential energy. Right, so we cannot use this lower the potential energy strategy. That being said, now we use a new and actually quite naive idea. So let's just add a small bubble here, which is only supported near this tiny neighborhood of a point. And such that, well, the support is small, and then we want this bubble to have its, to be something like this, which have its C1 norm to be of order 1. Okay, so for a bubble with its C1 norm of the maximum gradient of order 1, when the maximum gradient is of order 1, because the gradient here is also of order 1, it means that, well, this could beat that one, right? So that we just want the level set to be forming a small loop here. And so once the level set is forming a small loop, it means that, well, for all the time during the evolution, because it is transported by a smooth flow, assuming it doesn't blow up in finite time, then the small loop may be deforming, but it will be remaining there for all the time with the same area. Right, and for that reason, the presence of this loop for all the time will make the density to be never able to get too close to a perfect stratified state. And actually, we can show that again that the partial x1 will have its integral to be uniformly bounded below by a perfect constant. And again, what does it mean? It means that if partial x1 has a tiny h-1 norm, but its L2 norm is always can't get too small, right? It's always bigger than a certain constant, then its hs norm has to grow for any s bigger than 0. Right, so that is the idea for that we say that, well, even for this non-linearly stable steady state, if the perturbation is small in h2 minus epsilon, then we can still make it non-linearly unstable. Okay, so that's all I want to talk about. Overall, I would say the proofs themselves are easy, but they just are all based on this observation that the potential energy is going down, and when the solution is about to get quite close to stratified, then there are certain topological constraints that it doesn't allow it to be so, and that is the thing that causes the formation of small scales. So that's it. Thank you for your attention, and happy Lunar New Year.
Okay, let's thank Yao for the very nice talk, very interesting talk. Are there any questions? If you have a question, just unmute yourself and speak out, please.
Okay, I have a question.
Yeah.
All right, so yeah, so when you talk about the last one, the perturbation result, so your theorem says there exists perturbation. So my question is also following your construction, you added those bubbles. So my question is, like, how generic is the perturbation? So you have one, or actually you have kind of like a dense set, a generic set of perturbations, which will have this non-linear disability, instability. Sorry.
Let's see. Certainly that there are certain ways when you are adding your so when you are adding the perturbation, so for example, if starting from this row S where the lighter one is already on top of the heavier one, let's say suppose you just add some very heavy thing at the bottom, right? Then such thing is again going to be it's going to be stable, right? So so I would say that certainly one have to be carefully choosing like what perturbation do you add. So for example, if this small bubble here is not strong enough to create a loop in the level set, then we also have no idea whether there will be this nonlinear instability or not. Maybe it's going to be, so if it just creates a little winkle in the level set, but not just changing its topological structure, then maybe there's a possibility that it could just be eventually straightened out. Yeah, so we have no idea. But what we do know is that as long as the level set is no longer of this stratified structure, as long as the level set has a closed loop somewhere, then we know that it will lead to this infinite in time nonlinear instability for sure.
Okay.
Okay,
thanks.
Any other questions? Okay, so I just want to say that this reminds me of a work Drew and I had done about 8-9 years ago about the invasive damping. So the last part also about this bubble thing. One of the things we did was that near the QF flow, which is stable for the Euler equation, and later Masmoudi and Bedrosian proved that nonlinear invasive damping. But before that, we showed that if you take the Sobolev space to be rough enough, like H2 3/2 for and lower for the vorticity, then you have arbitrarily close, unstable steady state near the QF flow. Very much like in this situation, and the Kiselev was constructed.
Exactly. Actually, when we are writing this part, that so somehow we have this nonlinear instability in below H2, but then they have shown this nonlinear stability above H10. That reminds me of your, well, it's different equation, different type, but the spirit is similar in the sense that when the perturbation was in Javaret space, then they showed that there can be the invasive damping happens as time goes to infinity, right? But then when it is H 3/2, right? I remember, or below
for the vorticity,
shows that there actually exist these structures that never gets that keeps invariant in time, right?
Yeah. And also one of the corollary was the existence of the unstable steady state arbitrarily close to the QF flow in the HS space when S is less than 3/2 for the vorticity. So
I see.
In some kind of similar flavor here. Very nice talk. So any other questions? Okay, then let's thank Yao again.
Thank you.
Let me clap.